first let me give a motivation. In probabilistic reasoning, the tabular Bayesian with CPDs is a very common approach. However, the complexity is exponential on the maximum number of causes per variable in a family. Instead of CPD, we can apply local models such as NAT-Modeled to reduce the complexity to linear. Therefore, our study of learning NAT-Modeled Bayesian structure from data is desirable. The BD score can learn a tabular Bayesian structure from data. It applies a scoring function shown here. To calculate the likelihood, we can apply MetaNet. This is an example. And we assume data D is complete and exchangeable. For each record in D, the MetaNet will contain an instance of the base network G. And the parent CEDA in the MetaNet are independent from each other. Moreover, the PDF of the CEDA has a Dirichlet distribution. We can use exponent to calculate the expected value of CEDA. For example, this is the expected value of CEDA B1 given A0 in this example. And after observing the data D, we can update the expected value and got the posterior expected value of CEDA as this equation. Then we can calculate the likelihood as this equation. And this likelihood can be derived, and it is decomposable by the families and the parent configurations. Next, let me introduce the NAT model. The NAT model has two types of gates: the dual NAND gate, which encodes the reinforcement causal interactions. For example, turning the sparkler on or raining may cause the grass to get wet. If both causes are active, the grass is more likely to get wet. This is a reinforcement interaction. And the direct NAND gate can encode undermining causal interaction. For example, taking medicine M or N may cause a patient to recover from disease D. However, if take both together, it will reduce the effectiveness of both. Then, if both causes are active, the patient is less likely to recover from disease D. Multiple dual and direct NAND gate together will form a NAND tree. This is an NAND tree example. Here, C1 and C3 are undermining each other through the direct gate G1, and the C1, C3 together reinforce C2 through the dual gate G2. With this NAT structure and the single causals provided here, we can get the CPD as shown here. The CPD of BN can be uniquely defined. And note that the probability here is consistent with the causal reinforcement and undermining. For learning NAT-Modeled the BNs, we derived the extended BD score as shown in this equation, and I will talk about each of them in the following. To calculate the likelihood, we extend the MetaNet to the N MetaNet. For example, this is a N MetaNet. The family of C has two parents, A and B. Hence, the local model of C can be tabular, direct gate, or dual gate. And we use a variable omega C to represent the local local model type, like this. And if omega C is a tab, the situation is exactly the same as we discussed before. But if omega C is DI or DU, which means C is NAT-modeled, then we only consider the single causal parameters and ignores the multi-causal parameters. And the MetaNet satisfies these two theorem here. Then we need to extend the Bayesian estimate as well. We have three types of extended Bayesian estimates. Type 0 means the parent configuration has no active value. In this case, the value of BE is 0 or 1. Type 1, if the parent configuration contains exactly one active value. In this case, it is the same as the tabular situation. And the type 2, if the parent configuration has 2 or more active values. In this case, the type 2 BE can be derived from the type 1 BE. And we reordered the data D as this ordering so that the type 2 BE can be well defined. For example, omega C is DI, and we have the type 1 BE shown here. We can calculate the type 2 BE as this example, as this equation here. To calculate the local structure prior, we use this equation here, where DL is the description length of L. If L is a tab, the DL of L is the DL of the CPDs. If L is a NAT-modeled, then the DL of L is the DL of the NAT structure plus the DL of the single causals. To calculate the global structure prior, we have these two assumptions: the independence of parent sets between each families, and the independence of individual parents within a family. And we assign this simple form here, where pi is the parent of X. Note that this assignment will prefer a simpler structure, which is desirable. And we apply a heuristic search to simplify the searching through a large space of candidate structures. It starts from an empty deck, and in each round for a pair of variables, for example here A and B, we do one of the three operations: add, delete, or reverse. And for each round, it may change the local structure for up to 2 families. And we only updated the subscore of the changed families to simplify the calculation. And for a given G, there may have different choice of local model L, and we choose L which has the highest score. And we also conduct the experiment to check if the learned BN makes inference accurate enough and significantly more efficient than the equivalent tabular BNs. We first simulate B1, which is a fully NAT-modeled BN, and we derive the B2 from B1, which is equivalent tabular BN. Then we sample the data D from B2, and we learn the B3 from the data D. For both B2 and B3, we perform 10 rounds of inference. And the inference error is shown here, which is around 0.025. This means B3 approximate B2 sufficiently well. However, the runtime of B3 is shown here is around 36 times faster than B2 is shown here on average. So it is significantly more efficient. In conclusion, we extended the BD score to learn NAT-modeled BN from data. In particular, we extend the MetaNet and the BD scoring functions. And we also performed a heuristic search and conducted the experiment to show the accuracy and the efficiency of the extended BD score. Thank you for listening. And if you have any questions, you are free to ask.
So, I was on mute. So thank you very much. The organizers told me they wanted the questions to be asked at the end of the session. So okay. If you could please stay in the session, and then we'll do, after all the talks are done, we should have about 15 minutes for all four. So next we have Zhenyu Liao. Zhenyu, are you ready?
Yes.
Okay, so if you can share your screen. Okay.
Yes, is the slides up?
Yes, we can see it.
Okay. Yeah. Good morning, everyone. So today I want to talk about our empirical study of scoring functions for learning Bayesian networks in model averaging. This has been a collaboration with Charupriya, Dongshu, and Peter. So some context from our study. We are targeting the Bayesian network structure learning, especially the score and search paradigm. The score and search problem is defined as we are finding the graph that is maximizing a certain scores over the range of directed acyclic graphs. So specifically here, we are using the data to assess the scores for the structures. And the most popular scores are, one is the Bayesian information criterion, that is from the likelihood family. And the second score, as the previous presenter has introduced as well, it's the Bayesian Dirichlet family. And specifically here, the equivalence uniform scores is very popular among the Bayesian network structure learning. So the Bayesian Dirichlet equivalence uniform score does have one problem, is that it's not regular, which is discussed in a separate paper. So we will not expand here, but that is just the property of the score itself. The model averaging scheme. So why do we do model averaging, right? So basically, the model averaging will address the shortcomings of learning the best network. I guess normally we would just identify the best scoring network, but it has many shortcomings because due to the insufficient of data being the biggest concern. But here, the model averaging, we're studying two schemes. One is bootstrapping, which is a well-established scheme. And the other is credible set, which is we developed in a previous work. So the bootstrapping scheme, essentially we just sample the original data sets with replacement, and then we learn a structure with each sample. So this structure will be the optimal structure for that sample. And also most likely, this is learned using heuristic methods due to time constraints. And then we have a collection of optimal networks from each sample that allows us to calculate empirical probabilities of each edge from all the learned structures. And then afterwards, we can decide on whether the edge exists or not using some threshold. Alternatively, we can use the credible set method. So in this approach, we learn a set of near optimal networks that is within some base factors of the optimal network. And in this way, we also have a different set of networks, near optimal networks. And then we can sort of set the threshold essentially in a similar way as the bootstrapping method. So again, briefly on the scores. So here the first family is the log likelihood family. Essentially, they take the form of the log likelihood minus some penalty of the graph structure. And some of the most common ones are AIC, BIC. And a recent one is called the quotient normalized maximum likelihood. That is the recent proposal that we are evaluating in this work. The second family of the scores are called the Bayesian-Dirichlet family. The Bayesian-Dirichlet family essentially is a continuous multivariate probability distribution that is very applicable, like specific to Bayesian networks. And the scores are not used outside of Bayesian network, as far as I know. So here we evaluate the likelihood equivalent version of it. So the equivalent means that the priors are uniform for instantiations of the child parents' values. And to set up our experimental evaluation, we considered a wide range of datasets, both from the BNLearn repository and from the UCI datasets. So for BNLearn, we know that they are a collection of Bayesian networks, ground truth Bayesian networks. For those Bayesian networks, we can just use it directly to generate samples of various sizes. And then we considered 10 from the BNLearn repository. For UCI datasets, they are not Bayesian network datasets to begin with. So they are, like, we use k-nearest neighbor imputation first, and then we have to discretize the dataset through the MDL principle. And then we learn a single network from each score. For each score, sorry. So for all the scores under our study, we learned an optimal network, and we use that as the ground truth network to evaluate the performance. And then we generate samples in the same way as the BNLearn sort of ground truth Bayesian networks. In the end, for the UCI datasets, we considered 16 of them. And since we have 5 scores in our study, that means we have total of 80 kind of network score pairs for the ground truth Bayesian networks. And here is just a snapshot of what's under our consideration for the datasets. And as you can see that for the UCI datasets, they are of various sample sizes and a wide range of number of variables. And the same goes with the Bayesian network repository, as they have variable sort of number of variables in the network. So yeah, 76 is the largest one under our consideration. And so now we have the datasets. We need to evaluate the scores on the metrics. So we consider 3 metrics here. One is the classical structural Hamming distance. It's Bayesian networks specific to evaluate directed edges. So this is cost insensitive because it's an aggregation of all the missing extra or reversed edges. Second, we consider an F beta measure, which is a classical sort of cost sensitive measure for different balance of precision and recall. We also considered a weighted error rate, which is also a cost sensitive measure that is a direct play on false negatives versus false positives. And we also aggregate, since we have so many data sets, we need to aggregate the results. So the results are aggregated through a border count, which you assume that the larger matrix values are better, then each score is awarded points based on their rankings among the scores. And the points are summed up for each score in the end. So here is the results for structural Hamming distance. As you can see, like for the structural Hamming distance, the winner is using, I guess, bootstrap is on the left and credible set is on the right. So both of them have a clear winner within the UCI family and also within the BLearn family. And the difference is caused by what's the dominant error, essentially, in the structural Hamming distance. So for example, missing edges or extra edges could be the dominant factor there, and that affects essentially the relative rankings of the scores. We also have the F-beta scores. So F-beta scores consistent with the structural Hamming distance results means BDEU essentially dominates both the AIC and BIC scores here. And for credible set, we find the new score called quotient normalized maximum likelihood dominates the other scoring functions. And this is consistent. So both of the results are consistent with UCI datasets, but not with the BLearn dataset. So conclusions, our conclusion is contrary to previous conclusion that recommends Beek. We recommend QML for the credible set approach and the BDEU for a bootstrap approach. And we have done the comprehensive evaluation on the 4 scores, being AIC, BIC, QML, and BDEU. There are more results, detailed results in the paper, if you're interested. And our results are on much larger networks than all the previous works. And our metrics consider both cost-insensitive structural Hamming distance and cost-sensitive measures, as the F-beta and the error rate, the weighted error rate. And yeah, I think we will reserve the Q&A, but thank you very much for listening.
Thank you, Zhenyu. Yeah, thanks for.
Let me stop sharing. Yeah.
Okay. Yeah, I know it feels a bit odd to just move on like that, doesn't it? But
that's true. Yeah.
that's what they told me. We'll delay our gratification and we'll have even more fun later. Okay. So yeah, next Shamir, Khandaker.
Hello, can everyone hear me?
Some noise. Try again.
Hello. Hello.
Yeah, that's good. Thanks.
Yeah, can you hear me?
Yes.
Can you see my screen?
Yes, binary classification. Yeah.
Yes. So I'm starting. Hello, everyone. My name is Shamir Khandaker. Today, I will present our paper called Binary Classification with Minimum Observations. As we all know, that binary classification is a very important task in many applications, but one of the many problems with current methods for binary classification is that it requires a lot of training data. At least 50 to 90% of the data of every dataset is used for training. So we have come up with a solution that requires at most 15 observations. Our solution can be divided into 3 parts. First, we come up with an unsupervised ranking algorithm. Now, second, we come up with a class labeling algorithm. And third, we come up with an equation to calculate the theoretical confidence of our accuracy. So so at first, I will talk about the unsupervised ranking algorithm. This algorithm clusters the attributes into similar groups and updates the weight of the attributes based on their correlation coefficient. Initially, all the attributes are set in the positive cluster with weight 0. If a correlation coefficient is positive between the 2 attributes, it signifies that they attract each other to be in the same cluster. Otherwise, they repel to be in different clusters. For example, to have a more comprehensive understanding of the algorithm, let us look at the figure in this slide. This figure is split into 2 parts. The first, in the top part, all the correlation coefficients are positive, and in the bottom part the correlation coefficients are negative. So I will look at the top part first, then I will come to the bottom part. So in the top part, if you look at cell A, in cell A shows that if attributes Wi and Wj are in positive cluster and their coefficient is positive, then they should be in the positive cluster, and then their weight will be updated by adding the coefficient to their previous weights. This represents the concept that both the attributes attract each other to be more positive if they are in positive cluster and their coefficient is positive. On the other hand, if we look at cell B, then it shows us that if attributes Wi and Wj are in the negative cluster and their coefficient is positive, then they should be in the negative cluster and their weight will be updated by subtracting the coefficient from their previous weights. This shows that both attributes attract each other to be more negative if they were in negative cluster and their coefficient is positive. Now let's look at the cell C, where Wi and Wj are in different clusters. In previous ones, they were either in both positive clusters or in both negative clusters. But here, they are both in different clusters. So in cell C shows that if attribute Wi and Wj are in positive and negative clusters respectively, and their coefficient is positive, then Wi attracts Wj to be in the positive cluster and Wj attracts Wi to be in the negative cluster. Thus, the weight of Wi will be updated by subtracting the coefficient from its previous weight, and the weight of Wj will be updated by adding the coefficient to its previous weight. The idea of cell D is also very similar, except the Wi and Wj's position have been reversed. Now let's look at a cell where the correlation coefficient is negative. For example, here in cell E, the correlation coefficient is negative. So it shows that if attributes Wi and Wj are in positive cluster and their weight Wi is less than of Wj, and then their coefficient is negative, then that means that Wi and Wj repulse each other. They try to move away from each other. Thus, the weight of Wi will be updated by adding the coefficient to its previous weight. As the coefficient is negative, adding it to the previous weight Wi will shift Wi towards the negative cluster, and the weight of Wj will be updated by subtracting the coefficient from its previous weight. Again, as the coefficient is negative, subtracting it from the previous weight Wj will move Wj towards the positive side. The idea for the rest of the cells are also very similar. So I will just skip them and move to the next slide. Here is our algorithm for labeling the classes, how we have labeled the classes. This is our algorithm, how we calculate the accuracy. And this is our equation for how to calculate the confidence of the accuracy that we have just got through our model. Here, as you can see, the accuracy of the binary classification of the proposed model, this x value is basically our accuracy, and this n value is the number of observations that you're using for to calculate that accuracy. So here we are look at the results of what we have got. This is the result for the hard. We have used 6 different data sets to test our model, and this is the heart disease data set. To test this data set contains 14 attributes and 303 heart disease patients. And as you can see, our accuracy is outperformed the SVM and decision tree classifier, which has used decision tree classifier, which has used a lot of training data, but we are still outperforming them, and our value is also very equal to the random forest and very similar to the other models. Here in arithmetic dataset, it contains 109,446 samples and 187 features. Each feature represents a heartbeat signal, and the target column has values from 0 to 4. Here we, since it is binary classification, we convert 0 means that the patient doesn't have any kind of doesn't have a heartbeat signal, and the rest means that it does have heartbeat signal. So we are converting any value which is not 0 to 1, and then we're using that data set in our model. And we have compared our model with other different models, and as you can see, our method outperforms linear SVM, linear logistic regression, support vector machine, and logistic regression. It has been only been outperformed by random forest. Next, we have tested our dataset in the compass with the compass dataset. Test our model with the compass dataset. The compass dataset has 672 samples and 11 features. This dataset is usually used to find out a person's likelihood of reoffending. Its features includes things such as a 2-year recidivism, number of priors, etc. It has 2,202 samples whose target is positive, rest are negative. As you can see, we haven't really got very good results for this data set, but it is very close, similar to the rest, given the fact that we have used so few training data. Then we have used a data set called adult data set, and in this data set, this dataset has 48,841 samples and 14 features. This dataset is basically used to find out a person's likelihood of earning more than $50,000. So it after pre-processing the dataset, our feature size turns into 107. Of those features, 76% or less basically say that the person earns less or equals to 50,000, and the rest say that the person rest of the 24% says that the person earns more than 50,000. As you can see, we have got our result. It hasn't been able to beat the rest of the models, but given the fact that we have used so few samples, we have got quite similar results. Next, we have used our model in the dataset called drug dataset. This dataset has 215,063 samples and 2 features. This dataset is used to find out whether the rating of a drug is greater than 5 or not. This is the result that we have got for this dataset, and yeah. And next, we have used our model in the German dataset. German dataset has 1,000 samples and 10 features. This dataset is basically used to find out whether a person has a good or bad credit risk. We pre-process this dataset by changing the job, housing, savings accounts, checking account purpose into a one-hot vectors. We also use age, credit amount, duration features as it is. It turns out the feature size converts into number 27. Of the sample, 699 are good credit risk and rest are bad. So this shows you our result, which is not as good as the support vector machine or logistic regression or random forest, but it is very similar to the linear support vector machine and linear logistic regression. Anyways, so that is my presentation. Thank you, and hopefully at the end of the presentation, at the end of everything, we can ask questions to me. Thank you.
All right, thanks very much, Shamir. And then last speaker in the session is Jonathan. We can fire on all cylinders. People can put questions in the chat. I thought since we have this sort of panel format, maybe we could give first our presenters. We'll take a few minutes and see if the presenters want to ask each other questions. I noticed there were 2 talks on learning Bayesian networks. And then after that, we'll open it up. I just thought that may be a way to help us relate the talks to each other. So, sound okay? Oh, Sebastian is here. He's the big chair, so is that okay, Sebastian?
It's perfect. Perfect. So you know on Zoom anybody can raise his hand if he has a question also, or
yep.
As you say, the chat is also a way for people to ask questions.
Yeah, and I also have many questions, so but you know, it's mainly about the audience.
So maybe Oliver, you could break the ice while people eat up for questions.
Yeah, so let's see. Wow, yeah, where do I start? So going back to the Bayesian network, maybe for the first speaker, Wanrong, can you explain, talk a bit about what you think the advantages are of the NAT model? So for me, that looks like a particular way to define the conditional probabilities of parents given children. You know, are there advantages, for example, to using decision trees?
Sorry, could you repeat the question? I was.
Yeah, you were using the NAT model, right? With the NIN gates and the AND gates?
Yeah.
Right.
NAT model, yeah.
As a way to define the basically conditional probabilities of child nodes given parent nodes, right?
Yeah.
So can you speak to what do you think are the advantages of that model? You gave some results compared to tables, but what about, say, using decision trees or other possibilities for the local probabilities?
Okay. So for the NAT model, there are many different kind of local models except for the NAT model. But we choose this one since the NAT model has many advantages over them, such as it has a generality. There is like it has the noisy OR model is another local model, but NAT model can generalize it. And also NAT model can be applied for the multi-valued variables as well. And also it can represent both the reinforcement and the undermining causal interactions. But some of the local model cannot, they can only represent the reinforcement causal interaction. So that's the reason we focus on the NAT model.
I'm the co-author. Can I add to Wanrong's answer?
Yeah, please.
I want to just address your comparison with decision tree. So decision tree is essentially deterministic. So the NAT model is a probabilistic causal model. So relative to the CPT, the conditional probability table in Bayesian network is the most general. It can cover any possible probabilistic dependency, but the NAT model simplify that and reduce the total number of parameters from exponential to linear, but allows the cost to be either reinforcing each other or undermining each other and all the possible mixtures. So it has the distinctive advantage is it's still probabilistic, but it's significantly efficient than the conditional probability table.
Mm-hmm. Yeah, no, that's great. Yeah, I thought I'd seen quite a few of these local models, but this looks like an attractive new one. Any other follow-ups for the NAT model paper? We can come back to that later, but
okay.
Okay. I don't know. Should I ask a question about the second paper, or I don't know. Anyone can jump in. All right, maybe I'll ask a question then for Zhenyu.
Okay.
So Zhenyu, are you still with us?
Yes, please go ahead.
Yeah. So I was intrigued. So you saw this, there was a kind of, or let's put it this way. So looking at the scores and model averaging, it makes sense to me that BDEU would do well because it's a Bayesian score, right? It's already trying to use distributions over the parameter values and price. But then you were saying that the QNML does better, I think, for the credible set strategy. So that I found that interesting. Can you explain a bit, like, you know, why is there this, what is it about credible sets that doesn't work so well for BDU versus QNML? Sort of, why are you getting these results?
Yeah, I think, so for one part is that, so the bootstrap method, it's implemented in a BLearn, where the QML is not implemented there. So that's a like practical limit, essentially, in that sense. So that's why, like in the bootstrap method, we actually didn't have the QML there. And a second reason is that, so the BDU has been proved to be not regular. Not regular means that it tends to favor more complex structures. So in that sense, yes, as you imagine, like as you get to a larger networks, then that favoritism would essentially translates to like worse performance in terms of the metrics that we are considering. So this is why, there's that difference there. But BDU in Bootstrap, because when you bootstrap, you tend to sort of favor like sparse structures. This is not proved, but yes, it's like kind of intuitively that is essentially why it's not a big problem. So that's why like the BDU sort of works sort of better in the bootstrapping method. Yeah.
So maybe relating the two papers, do you have a sense, would your results change if you used a more compact parameterization, like with the NAT models, for example, offer?
Yeah, I think so. For the NAT model, I think the first author actually proposed a new sort of BD family score. So yeah, that is essentially a different score than what we evaluated here. And so I guess our evaluation is a little bit different because in the NAT model, the author sort of cared about the probability, I guess, inference errors. Whereas here we cared more about the edges, so whether the edges are present or not, and so all the metrics that we considered is with respect to edges. So this is the tiny difference there. The NAT model will have a huge difference. Will have a huge advantage in inference for sure because of the efficiency they have there. So that is the difference there, essentially.
Yeah, I can see that. It does seem attractive.
I want to add a little bit to what Zhenyu was discussing in terms of the comparison. As Zhenyu already mentioned, that our experiment comparison had a slightly different objective than theirs. So they treat the ground truth model as a golden standard, and then they learn something, and then see whether or not this learned model compare exactly as the ground truth. So in our case, we go to a different direction. So what we emphasize is, okay, we want to make sure the learned model can produce reasonably accurate posterior during inference, and at the same time to be significantly more efficient than the tabular Bayesian network. So that was our primary objective. So then if we really want to apply the similar comparison as Zhenyu's experiment did, then I think that you may consider this Hamming distance, right? It would be reasonably good, but it would not be always exactly the same. So in general, our observation is that in general, it is not always necessary for the learned model to have the exact same structure as the ground truth. However, there may be conditions under which this is necessary. So under what condition you have to learn the exact same structure in order to produce accurate posterior is one of our future research topic.
Maybe you should collaborate, discuss more.
Sounds good. Thanks.
Let's see. Maybe then I can ask a question for Jonathan. Quick question. I know I'm cutting into the coffee break, but I'm thinking probably no one except for me maybe wants the coffee break. Shamir, I had some, it looked like intriguing results. I had trouble getting the high level story. So you're looking at the correlations of your input features, and then how do you decide what samples to use somehow? Are you somehow throwing out samples that have highly correlated features, or? I apologize. I feel like there's something fundamental I missed. Yeah. No, we can't really hear you. Oh. At least on my internet, I think maybe it's not working. Shamir, sorry. Oh, now it's better. Okay. Yep.
Hello.
Yeah.
Yeah, can you hear me now?
Yeah, it's good now.
Yeah. So we are the number of samples that we're selecting. If you look into the algorithm, we're selecting them randomly from the training data set. We're selecting 15 samples randomly.
Oh. Okay.
Yeah.
I see. So
was that the question? I mean, I didn't quite get
yeah, yeah, that was good.
You asked how we are selecting.
Yeah. How would your method be different from something like principal component analysis, where you also try to sort of exploit correlations in the input features?
The main advantage of our method is it uses a very
okay.
And in that it tries to classify
okay. All right. Shamir, sorry, hard to hear. You know what? We're out of time, but the organizers have set up the gather town. I put this in the chat, and they're encouraging everyone. Instead of if you were here, we would all be going for coffee break now. So instead, they're saying we could go to gather town and talk more about Bayesian learning and NATs, and we'll find out more from Shamir how it's different from PCA. Yeah. Okay, so thank you very much to everyone for participating and for contributing. Okay, and I guess I'm going to leave the room and hope.
Yeah, thank you very much